here's our agenda. I'm going to introduce a little bit to set the stage of what we're going to be talking about. Then Dan and Dylan will present the Pantheon Plus sample for 15 minutes, then the new shoes and the local H0 measurement by Adam Rees, and Dragan Uterer will just discuss some perspective of the result, and there will be some time for a discussion and some moderated question and answer, although the question will be filtered, because if you ask something that is going to be in the papers, then the paper are going to be available in a few hours, so you'll find the answer there. So let me set up the stage. H0 is everywhere, and it's a very special number. It's a very special number in my view because in astronomy, and especially in cosmology, we measure mostly redshift and angles, but we think and we interpret the world and the universe in terms of distances, and that's where H comes in. We even invented measurements that are in units of H, the famous little h, it's 100 times little h. So H0 is a key cosmological parameter also for the following reason. Let's think about it. It is the present day expansion rate of the universe. So it's a relation between a recession velocity and a distance. And so if one does what is written in the Can, the traditional approach is to build a cosmic distance ladder, and these distances are done by calibrating different rank of the ladder, parallaxes, F8 supernovae, masers, TRGB, etc., etc., etc. But at the same time, and this is all done at here and now, a very low redshift, but at the same time, H0 is also a global cosmological parameter of a model. And therefore, it can be constrained by looking at the universe at the largest scales. And the strongest constraints come from looking at the earliest light that we see from the universe, the cosmic microwave background. And that number is calibrated, is heavily relying on early time physics, which is what we like because the universe was linear and it's very well understood physics. And also then the same imprint of this parameter can be then seen in the larger scale structure of the universe, and for the aficionado this is done via the baryon acoustic oscillation. The cosmic microwave background gives us a standard ruler. The numerical value of a parameter fit like on the right side of the plot doesn't necessarily need to coincide with what is the left hand side of the plot. And now the precision of both approaches start being very comparable. The two sides of error bar match. So this is precision cosmology. And this is the only parameter, cosmological parameter, as far as I know, where this can be done. So that's why the H0 game, it's a little bit of an end-to-end test of the universe. It's given the size of the error bar, it's like threading a needle from the other side of the universe and hitting the needle here and now. One important development has been, and that's why measuring H0 has important consequences for cosmology, is that the traditional cosmic distance ladder has been scaled and can be extended now all the way to the cosmic microwave background and back. And this is because the supernovae can be used as a standard candle, and they are very good at giving relative distances. On the other hand, the clustering of the baryon acoustic oscillation can be used to measure absolute distances if they are calibrated on the value of the sound horizon radiation drag, that is the standard ruler that is seen in the CMB data. So the traditional way to do standard ladder is to do the cosmological distance ladder to get to H0 and to get into the supernovae. Now the supernovae and the baryon acoustic oscillation overlap in redshift, and therefore they can be calibrated in terms of distances to one another, but the baryon acoustic oscillations are calibrated on the early time universe, that is the cosmic microwave background. And then, of course, one can also do the opposite and do the same thing the other way around. And what we've learned is that there's not much wiggle room in the middle. So now we have two ladders and therefore a tail of 2H. A priori, these two numbers do not have to coincide because we've done completely different type of measurement to obtain them. If they coincide, then the needle has been threaded from the other side of the universe, literally. And that means that the adopted cosmological models survive an extremely stringent test. On the other hand, you can ask, what if the two numbers do not coincide? Then I think we have three options there. There are errors in the data, there are errors in the analysis, or there are errors in the model. So the famous tension since about 2016 basically says that the local direct measurement of H0 tends all to land in the camp between 71 and 74 kilometers per second per megaparsecs. The early time physics calibrated measurement tends to land in the 68 kilometers per second per megaparsec camp, but the error bars are small enough that this difference is important and there is no much wiggle room in the middle. So of course, at the low redshift end, error, especially systematic error, therefore are becoming the name of the game. And you can visualize this error as how wobbly or stretchy this direct distance ladder may be. So I suggest to keep this in mind in the presentation, in the following presentation. The error bar size and the reliability really matter, and you will be able to appreciate the phenomenal amount of detailed work that went into producing the result, the control and propagation, all of sort of error, especially the systematic error. And the paper that will now be presented make this ladder much stiffer, much more secure, and dramatically less wobbly, so to speak. And without further ado, I give the floor to the next speaker. Please go ahead. We can't hear them.
Oh, can you hear me?
Yes.
Great.
Thank you.
All right, thanks everyone. Thanks everyone for being here. So thanks Licia for the great introduction. So this is going to now be two kind of small talks. The first part will be on Pantheon Plus that Dylan Brout and I will give, and then Adam will talk about the SH0ES and finally the H0 measurement. So this first side will be on how we use the Pantheon Plus supernova sample to make inferences about the Hubble constant. Okay, now we're really happy that everyone's here. We kind of realized that this had hit a different level when we saw even XKCD is talking about this. And just kind of for some numbers, as Licia said, the numbers that you have to keep in mind are kind of previous measurements of the Hubble constant, at least from the SH0ES side, were about 73, from Planck, kind of 67.5 or 68. And kind of the units are kilometers per second per megaparsec. So we'll keep talking in those units. Okay, so to expand on what Licia talked about, type 1 supernovae and Cephids, they're standardizable candles. And here I'm showing kind of two different ways for doing cosmological measurements. On the left, this is showing the distance ladder from the SH0ES team. So this is a 3-rung ladder where in the first rung, you're using geometry like parallax to calibrate Cephids. In the second rung, you're then using the brightness of the Cephids to calibrate the brightness of supernovae. And in the third rung, you're using the brightness of supernovae and the redshifts of the supernovae to measure the Hubble constant. Now, that third rung can be kind of expanded if you go to higher redshift. And if you can see on the right, and you make a Hubble diagram, and if you go to higher redshift, then you could measure other cosmological parameters like properties of dark energy. Now, what we spend kind of most of our time on in either the kind of Pantheon Plus or in SH0ES is to make the supernovae in the second and third rung, or for SH0ES, the Cephids in the first and second rung, as consistent and possible. So measure the same way, calibrate the same way, standardize the same way. And as long as you do that, if there's any systematic in supernovae or Cepheids, it will cancel because it's in two rungs. And that's really kind of what makes the distance ladder so powerful. Okay, so from a supernova perspective, really they could be used to measure the Hubble constant as part of the distance ladder, or they could be used kind of in this Hubble diagram to measure the equation of state of dark energy, which we call W, or kinematic terms of the expansion history of the universe, Q naught, J naught. And what you can see in this figure here, and these kind of, so far I've only showed kind of old plots, is that when trying to measure W, you're trying to use a large redshift range, and you're looking for a kind of small signal on a scale of about 0.02 mag. And over that large redshift range, a lot can change. You could have different surveys, different filters. You have to worry about evolution. Whereas for H naught, kind of the tension as it's been, it's about 10 times bigger than the signal that we're chasing after for W. And the scale that you have to worry about things changing is much smaller. You're really comparing supernovae for Z less than 0.01 to Z of about 0.05. So you really don't have to worry as much about kind of so many things changing like surveys or evolution. Okay, now I just want to give a schematic of kind of how we do this measurement with Pantheon Plus. So a supernova goes off in a galaxy, and we have to model the demographics of the supernova properties, the selection, kind of what we're discovering. Then kind of on the x-axis of our Hubble diagrams, we have to care about the redshifts. We have to account for any kind of peculiar velocities due to bulk flows in the nearby universe. Then we have to worry about how do our telescopes measure these supernovae. So we have to cross-calibrate all the telescopes, the different instruments and filters. We have to account for the different selection effects of every survey that has discovered and measured supernovae and try to model that. Then we measure and compile all the light curves of the supernovae. Then with those, you can see on the right side, just what some light curves of type A supernovae look like. And we use just a few properties of the light curves to standardize the light curves. And then from that, we could get distance measurements. So we have to determine the covariance of these measurements. And you'll hear a lot today about how we really strive to kind of do really good measurements of the covariance across all the supernovae. And then finally, we measure the cosmological parameters. Okay, so all of these steps we've tried to take on. So basically, 3 years ago, the Pantheon sample came out, and this we're calling the Pantheon Plus sample. And what we tried to do is we tried to look at kind of every facet of the Pantheon analysis and just try to do better. So all of these papers are out. I think the last of these 6 kind of sample and systematic papers have all come out. So you can see the archive links on the left. And a couple of things I just want to say, you can see kind of how many people worked on this. It's really been excellent contributions from a lot of people. And one of the things I'd say is that this is a compilation analysis. So we're using a number of samples and analyses that have kind of come before. So this really relies on a lot of work that people have done before us that have now spanned multiple decades. And lastly, I'll just say, kind of handing off to Dylan, that we're going to highlight important contributors, especially students who in the bottom right. So please look out for that. Okay. Sorry, I just want to mute.
Thank you, Dan. Okay, let me request control. Okay, so now I'm just going to dive in briefly on each of those papers that we've been working really hard on for the last couple of years, namely hitting upon the systematic uncertainties that we're really trying to control to make that ladder as robust as possible. The top level paper is, of course, the description of the data set and the compilation of what is now 1,701 light curves, ranging from a redshift of 0.002 to redshift 2.3. And so in comparison to the original Pantheon of about 1,000 supernovae, and the original Pantheon, as you can see on the figure on the top right, only went down to a redshift of 0.01, which means that importantly now in our sample, we are including the Cepheid host supernova calibrators in the analysis simultaneously with the Hubble flow set. So the second and third rungs of the distance ladder are now being analyzed simultaneously, and that includes systematic uncertainties and, again, the covariance matrix. What that means is that we've now compiled 18 different surveys, 25 different photometric calibrations of 105 different filters. And what that gets us is now an average of 2 photometric systems for every supernova that is in a Cepheid host. So that's 80 light curves for 42 hosts. So that really lowers our sensitivity to potential sources of systematic uncertainty, namely survey calibration, which we're, of course, always worried about. Okay, let's see. Oh, okay, so speaking of calibration, we've undertaken a large effort to cross-calibrate all of the 18 different surveys in our analysis, and we do this using the Pan-STARRS All-Sky Stellar Catalog, which we make use of because it covers 4 pi of the sky, and it overlaps with all of the surveys that we are analyzing. And we can use the stars to cross-calibrate the different surveys and get all of the supernovae on a consistent flux calibration. What this does is it gives us a new calibration solution, which means that we now retrain the supernova model given this new calibration solution for all the supernovae in the model itself. That's an important part of this analysis that we've now updated thanks to Georgie Taylor. And this also gives us a covariance matrix specifically for the covariance between every single filter calibrated in our analysis, which we also propagate to cosmological uncertainties, importantly. And ultimately, we find that the uncertainty in calibration itself is less than 0.2 kilometers per second per megaparsec in H0. And you'll see on all of the following slides, we have a blue quote. So if you take one thing away from these slides, it's a quote from the paper itself commenting on the uncertainty contribution and the systematic uncertainty contribution to H0. So a paper led by Anthony Carr and Tamara Davis dives completely into redshifts used for the sample. They do a general redshift update for every single supernova in the Pantheon set, Pantheon Plus set, excuse me. And that involves examining the host galaxy assignments of the supernovae themselves. It involves no longer doing CMB frame redshift approximations and correcting that, and doing peculiar velocity corrections. And among all the corrections they make to the redshifts in the Pantheon Plus sample over what had previously been published, they find a delta H0 of minus 0.1 kilometers per second per megaparsec. Eric Peterson and Darcy Kenworthy have done a deep dive on peculiar velocities. They've examined a number of different peculiar velocity maps and codes and applied them to our data set. What you can see here is in the figure in the green is viable models for peculiar velocities and consistent with what we have been doing in the past. So you can essentially ignore the red areas of the plots because they're simply for comparison. But when they examine a number of different peculiar velocity models and they examine the assignment of groups and to the redshifts based on clusters, they come up with an optimal combination of peculiar velocity maps and group assignments to apply to the data set and ultimately examine the different models and find that it adds no more than 0.17 kilometers per second per megaparsec to the uncertainty. Sasha Brownsberger has asked the question, well, what if there is some residual calibration error that we're simply not aware of and which we're always concerned about? And how would this impact the inference of H0 or, for that matter, other cosmological parameters like W and omega matter? And what he finds is that actually it does not appreciably affect the inference of H0 if you allow for potential extra survey-dependent calibration errors and allow them to be fit during the fit of H0 itself. It does not appreciably increase the contours and the constraints on H0. Unfortunately, this is not also true for W and omega matter. They don't benefit from this sensitivity. But in terms of your confidence in the distance ladder measurement of H0, it's something we can have a sigh of relief about. And lastly but not least, graduate student Brody, excuse me. graduate student Brody Popovic, has been working with extensive simulations that encompass every facet of our analysis. That is from observing strategy, cadence, weather conditions, and so on, telescope properties. And he applies them in a way that we haven't done in the past, which is by making use of some fast-forward modeling code that he developed, he is now able to apply these extensive simulations to fit the intrinsic properties of supernovae themselves and the relations to host galaxy properties. And he finds that when marginalizing over these possible relations and intrinsic variations, that they add no more than 0.15 kilometers per second per megaparsec. One other thing that I'll also note is that in the SH0ES paper itself, which you'll be hearing about shortly, Adam and others, what they do in order to combat the potential uncertainties due to supernova host relations, as we've said before, it's important to mitigate systematics by making sure the demographics of your sample are similar between the second and third rungs of the distance ladder, or first and second. But when you're talking about supernovae, second and third rungs of the distance ladder. And what he does is essentially trims down the Pantheon Plus sample to the most similar demographics between the second and third rungs to mitigate this potential systematic uncertainty. So you may see, we are talking about 1,700 supernovae in the Pantheon Plus analysis. You may see a different number in the SH0ES paper, and that's for this reason. So what does all this work get you? Well, it gets you the largest spectroscopically confirmed type 1a supernova Hubble diagram to date, which we're incredibly excited about. And we're using this to not only measure H0, but very soon we'll be releasing results for constraints on other cosmological parameters in the expansion history. And between the statistical improvements and improvements on all of the systematics that I've described, which include other things that I haven't mentioned, like improved analysis methodologies, improvements to the intrinsic scatter modeling, and of course the recalibration itself, we see a 2.2 factor improvement in the figure of merit over the original Pantheon, which we're incredibly excited to release soon. And so the last thing I'll leave you with before heading to the SH0ES paper itself is what we'll be releasing as part of the Pantheon Plus data release. This will happen on GitHub and also on our webpage, where you can see all of the papers and the links to the papers, and eventually the data itself, which will include light curve photometry, the SALT2 light curve fit parameters, the light curves themselves, the redshifts, distances of the supernovae and the Cepheids themselves, the Cepheid hosts themselves, covariance matrices, which at this point in measuring H0 and cosmology expansion history, you cannot avoid. We use covariance matrices throughout our analysis, including a supernova distance covariance matrix and a host galaxy Cepheid distance covariance matrix. We will be providing catalog level simulations to test your own analysis methodologies, whether that's to test them in a blind manner or to test for biases in your methods themselves. And then finally, we'll be releasing cosmology products like chains and likelihoods that you can get simply from public codes like Cosmosis. So with that, if anyone has any questions about how to use the data when the time comes, or if they would like to request additional data products that we don't have listed here or haven't released when we do, please do feel free to reach out to us. So with that, I'll leave it to Adam.
Okay. Can you see my screen okay? Okay. And I should be unmuted. All right, excellent. Well, I'm very excited to be here and follow the talks on Pantheon. I feel like we're standing on the shoulders of giants, except I realize with the distance ladder, that analogy is reversed. They're standing on our shoulders. That's okay. So I am going to present work on behalf of the SH0ES team and Pantheon as well on this new paper, a comprehensive measurement of the local value of the Hubble constant to 1 kilometer per megaparsec per second. Again, I want to express my gratitude to the SH0ES team. The members of the team in the paper are listed there at the bottom. And this paper should be available right after this telecon on the GitHub site that you see listed below. Okay, let me just first tell you a little bit about the SH0ES project. It was set up about 15 years ago to try to get a direct local measurement of H0 with HST to reach sort of percent level precision. We had a slightly different acronym. As they say about acronyms, all acronyms are wrong, but some are useful. And so I would say the story here has changed a little bit to, as Licha described, it's really an end-to-end test of the cosmological model. And so our goal was to reach this percent level precision calibration empirically by starting out by building a distance ladder that you've heard about with the sort of gold standard tools of cosmology, geometry, Cepheid variables, and type 1a supernovae. We saw ways to reduce systematic errors over past measurements by making purely differential measurements along the distance ladder. I'll describe that in a minute. And by making these measurements in the near infrared to reduce the effects of dust along the distance ladder, as well as strict propagation of statistical and systematic errors that can be done simultaneously and now with covariance, so we can get realistic error budgets. You may have heard of, there was two very successful generation 1 experiments with the Hubble Space Telescope to measure the Hubble constant to 10% precision, and those succeeded very well. This is really a generation 2 experiment. Unlike those which got a large allocation of time at the beginning, these were more pay-as-you-go, a series of 18 competed proposals starting 15 years ago that now, to our amazement, have accrued to about 1,000 orbits. Okay, so we're here to present results on the most recent and maybe last great doubling of the sample. And so HST can calibrate directly type 1a supernova hosts and type 1a supernovae by looking at, in this case, Cepheid variables in those hosts out to about a distance of redshift 0.01. And in the last 40 years, the era in which digital data is available for those supernovae, there's been about 42 such objects. They accrue only about once a year. And so what we're presenting is the first really complete sample of all of those that are possible to make these measurements. And so just looking at how that data accrued over the last 20 to 25 years, earlier releases were based on just a handful. A few we inherited from first generation experiments, up to about 8. In 2016, there were 19, and here is, we're more than doubling that sample. At the same time in this release, we're also more than tripling the sample of Cepheids that have been found in the geometric maser host. That's the first rung, or part of it, NGC 4258. At the same time, we are reprocessing all of the data with an improved pipeline and new reference files for the Hubble Space Telescope. A lot of this data has been processed in 6 or 7 years, and some of it as long as 15 years. So this is a very important step. So these are the sources of data that we are using along the distance ladder. We spent most of our time in the last few years improving the first rung. Some of this has come from external data. For example, Gaia parallaxes have been very important as one of 3 sources to geometrically calibrate Cepheids, as well as the masers in NGC 4258 and the detached eclipsing binaries in the LMC. And we've done a lot of work in observing the Cepheids in those places with HST. What you're going to hear about today involves, as I said, the big increase in the sample on the second rung, which is really the rate limiting step for us for measuring the Hubble constant because of the small size of that sample. And Dan and Dylan have talked to you about the Pantheon work that connects the second and third rung. And so we've gone through an exhaustive set of tests. We're exhausted at least. A comprehensive set of analysis of systematics. We've gone through 67 major variants of other ways to do the analysis, ideas people have had in the literature over the last 5 years, bifurcations and other splits of the data looking for anything interesting, and the full release, which will come out after the papers are in the journal, will be 10 million data numbers. I would encourage you, I would ask you kindly, actually, to read the paper. It's long, but you may have questions, and they may be in there, the answers. If you still have questions, please feel free to reach out to us and ask. And I want to highlight the work here of Wenlong Wan, who is a postdoc at Johns Hopkins University, who has really helped develop an automated Cepheid pipeline, which, as you can imagine, is very important for this work. And he's also the lead author of a couple of these papers coming out on Cepheids in 4258 and the discovery process of finding Cepheids. Okay, so let me just show you briefly a little bit about the new data. And so we have found Cepheids, the red dots you see, in the hosts of 22 new type 1a supernovae. Now, we have also observed Cepheids in the Milky Way, the Large Magellanic Cloud, and NGC 4258, as well as these Cepheids using the same instrument with C3 and the same set of 3 filters. That's what makes this a purely differential measurement. At the same time, this year, we have observed 4 new fields in NGC 4258, which has allowed us to more than triple the sample of Cepheids there. Here are the period luminosity relationships in each of these galaxies observed in 3 bands. This is how we measure the distance once the Cepheids are calibrated to these host galaxies. And here is evidence of these as Cepheids. In each galaxy, we can stack the light curves of all the Cepheids, and you see the characteristic rise and fall of Cepheid variables. If I can, just before getting to the cosmology, I would just want to show you something that's quite interesting and I think quite revealing, even in this data. When you look at the thickness or width of these composite light curves, you see that they're relatively thick. Some of that, of course, is caused from low signal to noise when you look at distant Cepheids. But some of it is because I'm showing you Cepheids that are over a range of periods, and the shape of a Cepheid light curve actually varies as a function of its period. This is something that was known almost 100 years ago by Ejnar Hertzsprung of the famous Hertzsprung-Russell diagram, pointed out that if you look in the Milky Way at individual Cepheid light curves, as shown here from short period to long period, there's a sequence of shapes of those light curves known as the Hertzsprung progression, as well as small scale features like this bump here shown in blue that migrates from the descending part of the light curve to the early part, whose physics is now well understood as a resonance between an overtone oscillation and a fundamental mode oscillation. Now, you would normally not be able to see any of this level of detail or features in any one distant extragalactic Cepheid. But if we now take, and this is just something we've recently done, if you take all those Cepheid light curves and you now bin them in period, you actually reproduce the whole Hertzsprung progression, but now seen for extragalactic Cepheids, the ones in the supernova hosts primarily, all the way down to some of these more subtle features of the second overtone resonance with the first overtone. And you see this whole change in the envelope of the amplitudes of these that nicely matches the Hertzsprung progression. And so this just simply answers the question as people ask, is there any way that extragalactic Cepheids could be weird or just different than Milky Way counterparts? And in more detail, they really look just like the nearby ones. Okay, so we measure PSF photometry. We do this with a pipeline. We inject artificial stars. We use those to measure the backgrounds. We also use them to measure the measurement uncertainties. And so what I'm showing you are the extracted artificial star measurements compared to a Gaussian, and the errors do look Gaussian to about 3 sigma. We go over that in great detail in the paper, and that allows us to do future statistics. Okay, photometry is a very important issue, measuring it well. And so in the paper, we provide 2 independent tests of absolute photometry, of the PSF photometry, one using apertures, which is relatively straightforward. The other is just comparing to what other groups get. And then we present 6 validation tests of the backgrounds or crowding of Cepheids. I won't take the time to go into all of those, but I wanted to just show one of them that's very visual. One can look, for example, at Cepheids in one galaxy in regions that are very dense where the background is high, like you see in the red, or in the outer regions where the background is very low and photometry is very simple, just a simple aperture will do. Because all these Cepheids have the same distance from us, you can compare these two, and what you see is that the ones in the dense environments and the outer environments, once they're corrected for the background, give very consistent distances to about 100th of a magnitude. Okay, so going to the baseline fit now of the full data set, 3,200 Cepheids, 300 some type 1a supernovae in the nearby Hubble flow with matched demographics across the second and third rung. And now for the first time, non-diagonal covariance matrix. So this is the distance ladder covariance matrix that characterizes the covariance between Cepheids in the same host. Those are the black squares due to background covariance. Cepheids in distant hosts because of the metallicity scale. And then, of course, the supernova covariance that Dan and Dylan talked about. And although this can be done analytically, we also did a large MC analysis so that you can look at the interrelationship between variables. There are 5 free parameters, the fiducial luminosity of our 2 standard candles, 2 nuisance parameters that characterize Cepheid variables, the slope of their period luminosity relation and the relation between luminosity and metallicity. And then the 5th parameter is 5 log H naught, or you could think of it just as the Hubble constant. Okay, so perhaps this is a number you were waiting for to see. So what we get from our baseline fit is 73.04 plus or minus 1.04, and that includes systematics. A shorthand summary of this might just be 73 plus or minus 1. And this is now 5 sigma from Planck plus lambda CDM, and it's a good fit to the data. Now, let me just show you samples from the posterior of our MC analysis compared to the Planck posteriors. And so here is the baseline fit compared to Planck. And here we take the log just so you can really zoom in and see the tails. So we've done at least 100 million samples so that we can get out to that 5 sigma tail. One thing that you might notice is the uncertainty in the low H naught direction is smaller than in the high H naught direction. It actually drops below 1 here. That's just simply because our measurement is natural in the log of the Hubble constant, or 5 log H naught. So therefore, it becomes smaller in this direction. Our baseline fit gives 1 kilometer per second uncertainty. Compare this to in 2016, it was at 1.7. And in just last year after Gaia, it was 1.3. Okay, so questions people might have, things they might wonder about is, for example, are the 3 different routes to geometrically calibrating Cepheids consistent, the anchors? And the way we address this in the paper you can read about is to use any 2 of the anchors, exclude knowledge of the 3rd, but use the distance ladder to predict its distance. And so we do that for each of the 3, NGC 4258, the Milky Way, and the Large Magellanic Cloud, comparing the independent measurement to the distance it should have according to the distance ladder, but not using that distance. And those all agree to better than 1 sigma. So there's good agreement there. The reason that there's good agreement is seen in one of the nuisance parameters of the distance ladder, which is the relationship between Cepheid luminosity and metallicity. There is seen a strong relationship between the Magellanic Clouds, NGC 4258, the Milky Way, even internal to the Milky Way, using Gaia parallaxes. There's a range of metallicities within the Cepheid sample in the Milky Way that are all in very good agreement. However, what's important is that this really doesn't have any impact on the Hubble constant, and the reason is because the metallicities of the Cepheids live within the range, really quite close to the mean, of the 3 anchors. And so when you look at the marginal or posterior from the MC, you see the relationship between the metallicity dependence and the Hubble constant is quite flat. And so the metallicity term explains the consistency of the anchors. It doesn't drive or cause a change in the Hubble constant. Okay, a very important crowding or null test we do is to compare the fit residuals for the Cepheids to their background. Now, the backgrounds are not part of the model. The backgrounds are part of the local measurement. That's what makes this a powerful test, is that the model doesn't know about the backgrounds. And so we do that in the for the Cepheids in the supernova hosts and the Cepheids in NGC 4258. Now, the data passes that. It's quite consistent with 0. However, you might think, what does it take for it to not pass that test, and in particular, to solve the Hubble tension? What it requires is to be systematically underestimating the backgrounds for Cepheids in supernova hosts, as would follow this red line here, so that it became 0.2 of a magnitude by the mean, or alternatively, to overestimate the background for the Cepheids in NGC 4258, since that's the calibrator. It goes the other way. And so you're looking for the black points to follow the black line, or the red points to follow the red line, which they clearly don't. In fact, it would be kind of bizarre and hard to understand why one would misestimate the background in one direction for one set of galaxies and in another direction for another. And in fact, the data show that we're pretty spot on in terms of the level of background. Okay, so some people will, rather than just take a value of the Hubble constant, will want to make use of this information to not only determine their own value of the Hubble constant, but to do that in concert with a cosmological model. There's been a lot said about this recently. And so the way we imagine people doing this is we will also provide just the distances to the hosts of 42 supernovae based on just the first 2 rungs of the distance ladder. So that's a set of those numbers plus the covariance matrix of those host distances. Then, if you want to do your own fit in cosmology, you can take this set of distances and their covariance and associate these distances with the standardized supernovae they host, as well as standardized supernovae in the Hubble flow, with these connected by just the calibration parameter, capital MB, the luminosity of supernovae, and of course having all the free parameters you want in your cosmological model, including H0. So when you do this, you're simultaneously solving for H0, the calibration that unites these 2 sets of supernovae, and the cosmological model for H of Z. I just do a simple example here that you can find in the paper, where you make that parameter Q0, the simplest sort of one parameter that you can also see relates to omega matter. And in this case, you get a very similar value for the Hubble constant. It doesn't have very much impact on the uncertainty in the Hubble constant. Q0 is around the canonical value, and you can see the correlation here, or relation between Q0 and H0 is very slight. Okay, so the heart of the paper really is going through all of these categories of variance and alternative analyses. We go through 12 categories, 67 variants. This is a plot from the paper showing the different values of the Hubble constant compared to the baseline. And so we vary how you reject outliers, how you use Cepheid colors to infer dust, the form of the period luminosity relation, which metallicity scale you use, or none at all. We also make use of TRGB distances in the paper. We spend a lot of time on this in the paper. We show that TRGB distance measurements are very consistent with Cepheid measurements when you start at the same anchor and go to the same supernova hosts. And so we can include them then simultaneously with the entire distance ladder, which does sharpen things up a little bit more. I could say more about that in the conclusions. You can change the Hubble flow sample, the calibrator sample, all in ways that test different aspects of the distance ladder, exclude different supernova surveys, different ways of doing supernova fitting, use of different peculiar velocity maps, or you could discard the near-infrared data and only use optical data. And so what I'm showing here are what I think are maybe some of the most interesting comparisons and checks that you might want to do. For example, people have proposed that we live in a giant void out to redshift 0.06, so we can start the Hubble diagram beyond that. Or again, another test of crowding is to just split the sample by the most crowded half or the least crowded half. Different kinds of dust laws. You can, as I said, go through these sort of at your leisure. But our bottom line here is it's very hard to get the Hubble constant below locally 72.5. very hard to get it above 73.5. We propagate an additional systematic uncertainty due to the variation of these variants. Most of this systematic uncertainty is now contained in the covariance matrix formally, so it's part of the error bar there. Okay, so this is the evolution of the error budget for SH0ES. This is actually starts with the key project to show that here, these are actually the full errors and these are the individual terms. And so in this most recent iteration, we see the biggest improvement since 2011 and 2016 because of more than doubling the sample. All the individual terms now are below 1%. Looking ahead, Gaia data release 4 and 5 will help on the absolute calibration side. But with 42 type 1a supernovae calibrated, or 46 if you include TRGB that are unique, and with them accruing, or I should say nature produces them only about once a year in the volume we can reach, it's unlikely this sample is going to be doubled again. So in some ways, this is sort of HST's, I would say, last stand on this. Okay, so my main conclusions here are the baseline result, which I quoted, 73.04 plus or minus 1.04 with systematics, some joint simultaneous analyses with TRGB, 72.5 plus or minus 0.99, or you could sort of go all in with other local measures that have been published recently. But again, doing this self-consistently, so you're not double using any data, and you're using consistent calibration, Mazur's SBF, 72.6. The values change only a little bit. The error bars come down. This doesn't really help you with the tension. In fact, it actually makes it a little bit worse. So this exceeds Planck by 5 sigma, or what we would call 1 in a million. Some other lower level sort of conclusions that may interest you. The extragalactic Cepheids really do look like the Milky Way counterparts, even in greater detail. The individual geometric anchors are consistent with each other at better than a sigma. This is a consequence of the Cepheid metallicity dependence. We've done a pretty thorough job, I think, now of matching the supernovae across the second and third rungs in terms of host types, properties, and surveys, which is contained in the paper. We find Cepheid and TRGB distances are consistent when you start at the same anchor and go to the same set of hosts. There's small differences in how you calculate the Hubble constant, which we go into in the paper. An exhaustive study, I think, of systematics variations have not yielded any indications of internal consistencies. We don't see any evidence of excess noise or unrecognized error. And my last conclusion is the source of the Hubble tension, to us at least, remains unknown.
Thank you, Adam. At this point, maybe Dragan wants to keep. Yeah, thank you.
Can you see my screen?
Yep, Joy, we can.
Yes, okay.
We can see your screen, but not your presentation. Now we see your presentation.
Okay. Hi, everyone. I am Dragan Hutterer. I am a general purpose cosmologist. I'm not part of the SH0ES team or the Pantheon team. And I want to say a few words why I and we cosmologists are so excited about these new results. Before I talk about the Hubble constant, let me say a few words about the new Pantheon data described in the Skolnick paper and a few of the other papers that are coming out. So here's a histogram of supernovae, and the dark blue is the new Pantheon data. You can see it's a lot of data at low redshift. This is a pretty major new development. It's really useful for some of the most basic tests of the cosmological model. First of all, dark energy constraints will benefit from the new data. Low redshift supernovae are actually particularly useful for this because they anchor the Hubble diagram, or in other words, they provide a measurement which can be compared to the high redshift the supernovae in order to better pin down the shape of the magnitude redshift, the shape of the Hubble diagram, which informs about the cosmological model. Those papers are forthcoming. Then peculiar velocities, the redshift you observe is related to the distance. They differ by the peculiar velocity term. So if you measure the redshift at low redshift, and if you know the distance because it's a standard candle, then you can have a pretty high signal-to-noise of peculiar velocities, which can be used to probe the velocity field and the local density field. So this is another basic test of the model. Finally, tests of isotropy. If you take distance, measure distance to a supernova in a given direction, subtract the mean distance, you get these distance residuals. Are they isotropic or not? That informs about the isotropy of the universe. So all these tests really benefit from supernovae and really rely on the fact that these supernovae come from a uniform sample. That is to say, you can see on this graph here, they come from all kinds of different surveys that have now been analyzed in a single framework. And that's a really pretty big new development in cosmology. On to the Hubble constant. So here's the new, I think this is actually quite a nice Christmas gift. I know we're supposed to get from our family members like a box of chocolates or a new wallet or some book to read. But to me, this is really as good or better. The new data, the new constraints on the Hubble constant. Here's a constraint from the new Rees et al. Paper that Adam just quoted. Here's the Planck results. They now differ formally at 5 sigma, just these two numbers. And I think this is a very important step in cosmology. This is a premier challenge for the cosmological model. In my opinion, it's the single most exciting thing happening in cosmology right now because it may indicate new physics, much like for people at the Large Hadron Collider who are hoping to see a bump in their data that indicates a new particle. We're not quite as desperate as they are, we in cosmology, but we still very much welcome this development, which may indicate new physics. These data are, the analysis, at least was an outsider like me, is impressive. It contains many checks for all kinds of different systematics, employs full covariance, modern statistical analysis. Now, if you go to the literature, you'll find papers that reanalyze this with even more cutting-edge statistical tools. They find the same results, so it's definitely not the statistics that's an issue somehow. In fact, overall, there's very little wiggle room left. Many things have been checked out, and this reminds me of the trajectory of type 1a supernovae that I used for dark energy. Now, in the late 1990s, I was a graduate student. These epoch-changing supernova results came out, and there were lots of questions. Did you forget about the evolution of a supernovae? What about different types? Is the CCD response linear? All kinds of questions were being raised that were answered in the following 10 to 20 years by more data, more careful analyses. Similar thing has just happened for the Hubble constant measurements. This method really matured, and now it's at a very firm basis, and really no one thing was simply forgotten or has gone terribly wrong. So I think that's a really interesting development. In terms of theory, there are literally hundreds of models out there that attempt to explain this. However, there's only one really simple and compelling model. Now it sounds like I'm going to advertise my model. But no, this model is actually simply sample variance of cosmic variance. Let's say global Hubble constant is 67, but locally we may measure it to be 66 or 68. And in fact, is it possible that locally we measure it to be 73 just because we live in a void, in a slightly underdense part of the universe? So this is the only simple model. In fact, this is a guaranteed effect at some level. This model is completely ruled out, essentially because local measurements actually do probe a pretty big volume of the universe, so big that this sample variance effect is very small. In fact, this can be quantified exactly, and the sample variance is equal to 0.3 kilometers per second per megaparsec, which is 1/20th of the difference it has to explain between the distant local and global measurements. So in effect, this model is ruled out at 20 sigma. So it definitely cannot be operational in anything like a lambda CDM universe. And that leaves literally hundreds of other models that many of them are fairly fine-tuned. They struggle mightily to be a good fit to the data, and especially even if they're a good fit, they struggle to lift the global Hubble constant from 67 to 73. Most promising of such models seem to be in the direction of changing the pre-recombination physics, which, for example, is being explained in detail in this review paper by Knox and Milan. the Hubble Hunter's Guide. And the latest salvo on this is analysis of ACT data in Hill et al. So there are lots of developments on this front. I think in general, there's lots of new physics signatures in the data that we should and will be looking at, especially with the CMB data. So the forthcoming CMB data will be fantastic to look at the possible new physics that may explain the Hubble tension. Overall, I would say right now, there's no compelling solution from the theory end to the Hubble tension. The future is very bright because, as I mentioned, these forthcoming CMB measurements from ACT, South Pole telescopes, Simons Observatory, CCAT, and other surveys, they will be very important. Now, we don't suppose they will change anything. We think they'll continue to find 67 with smaller error bars, but who knows? Let's see what they find. And certainly they will shed light on these theory explanations for the discrepancy. Moreover, it turns out that the combination of light phase structure, BBN, and baryon acoustic oscillations, independently of everything else, pins down the Hubble constant. For example, you can see this DS paper. Moreover, strong gravitational lensing delays are also a promising probe. You can, for example, see this Holy Cow paper. This is still a maturing method. There are always concerns, in my opinion, about modeling of the lenses, but it's a method that's rapidly maturing in front of our eyes. For the local measurements, these distance letters is really the main game in town. Gravitational standard sirens are promising. I'm not sure they cleanly fall into global or local measurements, but the bright sirens where you see the counterpart, they are really quite promising, but there's only like one so far. And the dark sirens where you don't find the counterpart, but where you ask many galaxies to vote which one of you was the source of the gravitational wave signal. That's another method that I think will have really quite a tough time competing in terms of accuracy, especially. And you can take a look at this paper by my student Emery Trott, where he showed some challenges with that method. Overall, the forthcoming data from JWST in particular are likely to shed major new light on the problem. And I will conclude this by saying that this is not only a very nice Christmas gift, this is a major new developing cosmology. The new data and the new analysis particularly results on the Hubble constant. Licia, back to you.
Thank you. So I would like to thank all our speakers for today. We just come to the top of the hour, but if there are any urgent questions from the audience, maybe we can take 1 or 2 minutes to address them. Otherwise, this obviously left us everybody with a lot of food for thoughts. There is a question there that I see that asks whether it's possible that there's some unknown systematics in the Planck analysis. I mean, if you want, I can take that, and then you can further elaborate on that. So the fact that you get an H0, not with a sub% error bar yet, using early universe physics and going completely away with CMB data suggests that is not a problem with the CMB data. And I'm not saying that's a problem with Planck, but it's not also a problem with WMAP plus ACT plus SPT plus whatever. It goes away, it takes the CMB data completely out of the question, and the tension is still there. Obviously it's not 5 sigma because the error bars are a little bit bigger, but it's still there.
Ryan Keeley had a question.
Yes.
Maybe Dan could answer that.
Yeah. Does the inclusion of the calibrator, supernova plus covariant mean one doesn't have to worry about using SH0ES information as a prior on H0 versus a prior on the MAC?
Right, yes. Yeah, so the short answer is yes. So basically, now that we are giving the covariances and we kind of give the separable distances, you can kind of do the analysis how you like without using information that you don't want to use.
And since it's in Cosmosis, I think it will be easy as well. You don't have to think too much about it either. I think that's a pretty standard tool.
Yeah.
Okay, so thanks everybody. Oh, one last question. I don't know if Dan, you want to read that?
Sure. The question is, in the Pantheon Plus part, could someone clarify why sigma H naught from the color standardization method by Brody Popovic stands out, differs from the baseline? It is still kind of what Brody did and kind of how we are doing the standardization is kind of nominal to our analysis. So kind of what we do in Pantheon Plus is kind of what's used in SH0ES. Hope that answers. Happy to talk offline.
All right. If you have any more questions, please feel free to email.